there any questions over the homework? Any questions over the homework assignment so far? All right. What we're doing today is we are starting to solve logarithmic and exponential equations. Now, the first ones we're going to look at, we're going to talk about this here, the property of equality for exponential equations. Another way that this property is called, it's talked about as the 1-to-1 property. Now, the 1-to-1 property, or the property of equality, states if b is a positive number other than 1, then b to the x equals b to the y if and only if x is equal to y. And the reason this works is if we look at this here, 5 to the 3x minus 2 is equal to 5 to the negative x. Well, the base for both sides is the exact same. So the only way these two equations can be the same is if their exponents are also the same. So since the bases are the same, we can say that the exponents have to be the same as well. So this means 3 minus 2x is equal to negative x. And the only reason we can do this is because the bases, there's one base on either side, and they're both the same number. Since we have 5 to the 3 minus 2x is equal to 5 to the negative x, since the bases are both 5, we can set the exponents equal to each other. Questions on this here? Now we just have to solve for x. We need to get x by itself. So the first thing we can do is what? So are the x's on the same side? Because we need to get the x's together. Negative 2x plus 2x is 0, leaving us with 3, is equal to negative x plus 2x is x is by itself, so x is 3. Questions on this here? Now, if we wanted to check and make sure that this is true, we could plug 3 back in for x. So we just replace each x with 3 and see if both sides give us the same value. Now on the left-hand side, we have 3 minus 2 times 3. Well, negative 2 times 3 would give us negative 6. On the right-hand side, our negative 3 is just negative 3. And lastly, 3 minus 6 is negative 3, and yes, 5 to the negative third is going to equal 5 to the negative third. We have the same number on both sides. So let's look at the next one. 6 to the negative 2a is equal to 6 to the 2 minus 3a. Are the bases the same? Do we have one base on either side? Well, yes. So if the bases are the same, the only way these two equations or two expressions can be equal is if the exponents are equal. So 6 to the negative 2a is equal to 6 to the 2 minus 3a, if and only if negative 2a is equal to 2 minus 3a. So we just need to solve negative 2a equals 2 minus 3a. There are no powers attached to a variable greater than 2. We don't have a squared a cubed. So we just need to get a by itself first. We can add 3a to both sides. Negative 2a plus 3a is a. Our negative 3a plus 3a is 0, leaving us with 2. So a is indeed 2. Questions on this here? Questions on any of this so far? Look at a few more of these. 3 to the 2a is equal to 3 to the negative a. Are the bases the same? Yes, so since the bases are the same, and there's 1 on either side, it means the exponents have to be the same. So here we're saying that 2a is equal to negative a. What would we do first? We add a to both sides. Because negative a plus a is 0, and since there's nothing else left on the right-hand side, it goes to 0. 2a plus a is 3a. Divided by 3. 3a divided by 3 is going to be 1a. 0 divided by 3 is 0. Questions on this here? Two to the 2x plus 2 is equal to 2 to the 3x. Again, the bases are the same, one base on either side. So the only way these two can be equal is if the exponents, 2x plus 2, is equal to 3x. We can subtract 2x because we need the x's on one side, numbers on the other. 2x minus 2x is 0. Leaving us with 2. 3x minus 2x is x. X is equal to 2. Now, for the most part, we've dealt with some pretty nice expressions in the tops. Questions on this here? Let's look at these next two here. We have 6 to the 3m times 6 to the negative m is equal to 6 to the negative 2m. Are the bases the same? Do we have 1 on either side? No, we have 2 on one side, 1 on the other, yes? Now, properties of exponents state that if we multiply like bases, we do what? We add the exponents. So yes, all the bases are the same, but we need 1 on either side. We can't have 2. So our 6 to the 3m times 6 to the negative m, according to property of exponents, a to the b times a to the c is equal to a to the b plus c. When we multiply like bases, we add the exponents. When we divide like bases, we subtract. So by doing that simplification, we're able to get one base on either side. And really, we can simplify this a little further, because 3m plus negative m is 2m. Telling us that 6 to the 2m is equal to 6 to the negative 2m. The bases are the same, and we have 1 of each. Meaning that the only way these can be equal is if the exponents are. So we're going to add 2m to both sides. Because our negative 2m plus 2m is 0. Nothing on that side, so it is just 0, yes? 2m plus 2m is 4m. Questions on how we got here? So we can do the same as we did this one here, because we had one almost exactly like it a minute ago, yes? Zero product property. Do y'all remember what that was? Zero product property. If I multiply two things together and it equals 0, one of them has to be. So if we look at this here, we're saying that 4 times m equals 0, yes? Multiplying two things together to equal 0. Well, m has to be 0. Well, the other way we could have done this is just divide both sides by 4. 4 divided by m is m. or 4m divided by 4 is m, and 0 divided by 4 is 0. Questions on this here? All right. We feel good about number 9 before looking at 13. So if we look at 13, well, again, we've got these like bases here being multiplied, yes? So if I multiply like bases, we can add the exponents. However, 64 is not a like base with 4, is it? So if this would be nice, it'd be nice if we could be able to rewrite 64 as 4 to a power. Is there an exponent we can put 4 to that gives us 64? Okay. 4 to the 8th is 4 to the 4th. The 4 to the 8th was too big. 4 to the 4th is still a little too big. 4 to the 2nd, 16. 4 to the 3rd is 64. So even though the bases, we start off with 2 on one side and 64 on the other, if we can rewrite them as the same base, rewrite 64 as 4 to the 3rd so that both bases are the same, we can still use this property. So since 64 is 4 to the 3rd, we can replace it because 4 to the 3rd and 64 are the same. And the reason we do this is now that we have done it, the bases are the same, so it means our exponents have to be the same as well for these two equations to be equal. So we're setting negative 2x plus x equals 3. Well, negative 2x plus x is negative x is equal to 3. Well, to solve this here, we can do one of two things. We can divide by negative 1, telling us x equals negative 3. Or we could have multiplied by negative 1, and it told us x equals negative 3. Questions on this here? All right. Let's look at the next two here. So our next one, 100 to the x is equal to 1 over 10 to the x minus 3. So we need the bases to be the same. We need a way to get the bases to be the same so we can set the exponents equal to each other. Well, on the right-hand side, this 1 over 10, if we can get it away from being a fraction, it's going to make it nicer or easier to work with. And we're able to do that by moving this 10 from the bottom of the fraction to the top. But anytime we move a number above or below a fraction bar, the exponent goes from positive to negative or negative to positive. So 1 over 10 is the same as 10 to the negative first power. 10 to the negative 1 is the same as 1 over 10. Or 1 over 10 to the negative first power is 10. So we're able to do this switch, which is going to give us a base of 10 on the right-hand side. Now, is there a way that we can change 100 to be a base of 10, or 10 to a power? 10 to what power is 100? Because 10 squared, 10 times 10 is 100. Now are the bases the same? Yes, and that's what we wanted, because it makes it nicer when the bases are the same. Now, before we can start setting anything equal, we do need to simplify some of these parentheses. Now, on the left-hand side, we have 10 to the second power to the x. Powers of powers multiply. So our 2 to the x is going to be the same as 2x. On the right-hand side, we have 10 to the negative 1 to the x minus 3. So really, we have negative 1 times our x minus 3. Negative 1 times x minus 3. Negative x minus 3. Now, since the bases are the same, and the only way this could work and be equal is if the exponents at negative 2x is equal to negative x minus 3. Now, before we're able to add or subtract, we do need to distribute this negative through. So the left-hand side will stay 2x. Now, our negative times x is going to be negative x, and our negative times negative 3 plus 3. Now, again, we don't have any squares. We don't have x squared, x cubed, x to a power greater than 1. So we need to get x by itself first. So we can add x. 3x equals 3. And last but not least, divide both sides by 3. Minus x is equal to 1. And that's it. Because if we can get those bases to be the same, we can set the exponents equal to each other and solve from there. Questions on problem A before we look at problem A? All right, let's look at the next one here. Now, again, the bases aren't the same. We have 81 to the x is equal to 1/9 to the x plus 3. As we just saw, it might be nice to get that 1/9 from a fraction to a whole number. And again, we can move that 9 from the bottom of the fraction to the top. Gives us 9 to the negative 1. Now we can change 81 to 9 squared, because 9 squared is 81. And the reason we're using 9 is so that the bases are both 9. We have the bases the same. And since the bases are the same, that means that the exponents are going to have to be the same as well. Now, before we start setting it equal, again, we have powers of powers. So 9 to the 2 to the x is the same as 9 to the 2x. Over here, 9 to the negative 1 to the x plus 3. Really, at this point, we could distribute that negative 1 through. Negative 1 times x is negative x. And negative 1 times negative 1 times 3 will give us negative 3. And again, since the bases are the same, the exponents have to be the same as well. Add x to both sides. 2x plus x is 3x. It's equal to 3. Divide by 3, telling us x is equal to 1. Ah, thank you. I don't know why I put positive. It would have been, yep. So it should be negative 1. Yes, thank you. Yeah, I don't know why I flipped it. Yeah. Questions on these here? Do we feel pretty comfortable with these here? Yes. All right. Do we want to look at 3 or the other one up here? 7. So I added that one in today. Let's do the 7 one here. Let's do this one. And I want to do this one on the right because it does apply a few properties to it. It's not anything really different than the number 3 problem. It just looks a little different. Yes. Now, just like 3 in this one here, the bases are not the same. And for us to be able to use this one-to-one property, we need to be able to write 343 as 7 to a power. What power do we think we need to put 7 to get 343? 4. Seven to the third is 343. And yes, 7 to the second power of 7 squared would be 49. So again, we're using this one-to-one to get there. Now on the left-hand side, we do have 7 to the 2x minus 3 still. On the right-hand side, we do need to simplify this power. Powers of powers multiply. So we can multiply through the 3 with the x plus 4. And 3 times x would give us 3x. 3 times 4 would give us 12. Again, bases are the same, so the exponents have to be the same as well. So 2x minus 3 is going to equal 3x plus 12. Now we need to solve for the value of x. Now, again, we don't have any quadratics. We don't have any x squared terms. So we just need to get x by itself, the numbers by themselves. We can subtract 2x from both sides to get the x's on the same side. Because over here, 2x minus 2x would give us 0, leaving us with our negative 3. 3x minus 2x would give us x. And have x plus 12. And then we would subtract 12 from both sides. Telling us x is equal to negative 15, or negative 15 equals x. Questions on any of this here? Questions on anything we've done so far? All right. Let's look at the other part of this lesson. Property of equality for logarithmic equations. And this is the same thing. This is our 1 to 1 property. If b, x, and y are positive real numbers with b different than 1, then log base b of x is equal to log base b of y if and only if x is equal to y. So what this is saying is if, the highlighter, our logarithms, we have one log on either side, and it's the same log, well, the only way this can work is if what's inside both logs, both of these logarithms, are the same, they are equal. Because if the logs are the same, what's inside them have to be the same. The only way the natural log of 4x minus 7 is equal to the natural log of x plus 5 is if the value of 4x minus 7 is equal to the value of x plus 5. The only way we can have two logs equal to each other is if what's inside each log is equal. So really all we have to do is solve 4x minus 7 equals x plus 5. We can subtract x from both sides. 4x minus x is going to be 3x. And we still have our minus 7. Equal to x minus x is 0, leaving us with our 5. We can add 7 to both sides, telling us 3x is equal to 12. And last but not least, we would divide by 3, telling us x is equal to 1. And that's it. Now we do need to be careful with natural logs and logarithms because the number or value inside the log here cannot be 0 or negative. And it's not so much that the value of x can't be 0 or negative. When we plug it back in, that value cannot be negative. So if we wanted to check this, what we need to do is just plug 4 back in. So we'd have the natural log of 4 times 4 minus 7 is equal to the natural log of 4 plus 5. Now the nice thing for us here is we can take either calculator and solve it, or we can simplify what's inside first. 4 times 4 is 16 minus 7. On the other side, we have the natural log of 4 plus 5, which is 9. Now our natural log of 16 minus 7 would be 9. And the natural log of 9 is indeed equal to the natural log of 9. Our final number inside both logarithms is a positive 9, which isn't 0 or negative, telling us that x is indeed equal to 4. Questions on the first one before we look at the next one? So again, natural log of 7x minus 4 is equal to the natural log of 2x plus 11. We have one log on either side, and they are the same logarithm. And the only way these can be equal is if what's inside each logarithm is equal, which means that our 2x plus 11 has to equal 7x minus 4. What can we do first? We can subtract 2x. 7x minus 2x is 5x. We still have our minus 4 is equal to 11. Again, x is not by itself yet, so we can add 4. Negative 4 plus 4 is 0, telling us that 5x is equal to 15. And lastly, we would divide by 3, telling us x is equal to 5. Oh, 5. Yes. Flipped my numbers. Should have divided by 5, which, yes, tells us that this is 3. Divided by the solution, not the number we actually needed. Questions on this here? Do we need to see another example one of these? We feel pretty comfortable with this. Let's definitely look at one of these two here. Yep. Bring them on in. Yep. Thank you. All right, guys, do you all want to look at problem number 11 or problem number 12? We'll look at 11. Log base 12 of v squared plus 35 is equal to log base 12 of negative 12v minus 1. Now this one here, we don't have natural log on both sides, but both of the logarithms are the same. They're both log base 12. So since our two logs are the same and we only have one on either side, it means what's inside these logarithms has to be equal. The only way that these two logs will be the same is if v squared plus 35 is equal to negative 12v minus 1. Now this here is the first problem that we have where we have a quadratic term, a v squared or x squared term in the equation. And whenever we have this squared term, this variable squared, we need to get the equation equal to 0. So we can add 12v to both sides. V squared plus 12v plus 35 is equal to negative 1. And yes, I did for some reason write x on the note sheet instead of v. But the result is still the same. Now at this point here, the equation isn't equal to 0, so we need to add 1 to both sides. It'll tell us that v squared plus 12v plus 36 is equal to 0. Because once we get everything equal to 0, we now have a quadratic. And we can solve this in several ways. We can use quadratic formula, we can factor it, or graph it. Which one do you all want to use? We can factor this. So we'll have our two sets of parentheses with 3 spaces because there is no greatest common factor between v squared, 12v, and 36. Since the third term is positive, our signs are the same and match the sign of the middle term. Factors of v squared are going to be v and v, because that's the only set of factors for v squared. Now factors of 36, we have 1 and 36, 2 and 18, 3 and 12, 4 and 9, 5 doesn't work, but 6 and 6. So we can do 6 and 6. And this here, if we did check it, it would work. Because v times 6 is going to be positive 6v. 6 times v is going to be another positive 6v. And 6v plus 6v does give us the positive 12v middle term that we wanted. And lastly, to solve, we're going to use the zero product property that states that anytime we have two or more things multiplied together to equal 0, one of them is going to have to be 0. And incidentally, when we solve both of these here, we end up getting that v is equal to negative 6 in both cases. Questions on how we solve this here? Now again, we said what's inside logarithms cannot be negative or 0. So if we check this, we go back and check it. Log base 12 of negative 6 squared plus 35 has to equal log base 12 under negative 12 times negative 6 minus 1. And let's see if they are the same and positive. Now on the left-hand side, our negative 6 squared, negative 6 times negative 6 is going to be positive 36. On the right-hand side, we have negative 12 times negative 6, which is going to be positive 72 minus 1. Now this here, 36 plus 35 is going to be 71. And 72 minus 1 is 71. So when we plug negative 6 in, even though the value of x was negative, when it's plugged back into the original function, the number that we finish up in each of the logarithmic spots, one, are the same, and two, none of them are 0 or negative. Because if the value of x causes this number, where 71 is, in this case, this final spot to be 0 or a negative, it would be an extraneous solution. We have to throw it out. So here, v or x is equal to negative 6 is our solution. Even though it does show up twice, it is our one main solution. Questions on this here? And that is it. So 5 through 8, 11, 12, 21 through 24. So 8, 11, 12, 21 through 24.